All right. So today we're going to go over support vector machines. So what's that, section 36? For the most part, this is kind of going to be our last stop at kind of like a supervised learning classification before we go into more unsupervised learning, which is next section is section 37, is PCA, principal component analysis, and section 38, which is clustering. So kind of classic unsupervised learning. So support vector machines was kind of like a big thing, particularly in the 90s, where it was kind of like really revamped. It's like, oh, wow, like we can do a lot of classification and it works really well. There's a lot of like benefits for support vector machines. One thing, for example, besides just classification, it actually can do a good job of making boundaries between different classifications. So you remember like our decision trees, when they try to make a boundary, they're kind of, it's kind of jagged, right? They're not the best boundary. There tends to be a lot of overfitting. We can alleviate some of that with ensemble methods, like using things like what's called a random forest. And turns out even vector machines or support vector machines, SVMs, I'll use that a lot, can be used in an ensemble as well. So sometimes you'll see ensembles use support vector machines. They tend to be a little more memory intensive. So usually decision trees tend to be done a lot in random forest because they're really quick and easy and straightforward. Support vector machines tend to have a little more overhead. So you don't see them as commonly in an ensemble methods, but they definitely can be used. So that kind of goes into what is support vector machine and everything. So let me go ahead and share my screen. And there's going to be two different notebooks we're going to go through. And I will say is that as great as the curriculum can be sometimes, I do think this section in particular can be a little unclear. I think there's a lot of focus on the mathematics, which in my opinion isn't necessary for this part of to really understand what support vector machines are doing. So note that even if you had gone through the material, note that I'm going to approach it in a slightly different way. And hopefully that will kind of give you a little bit of the math background from the curriculum and also a little bit of like higher level conceptual understanding. Okay, so let's get right into it. So let me make this, I'm gonna make this screen a little bit bigger so I got room to spare. Okay, and now Giovanna's here, awesome. Okay, keep going. So support vector machines. So first of all, I love this t-shirt, I think it's really funny. So support vector machines are a thing by itself. There's another supervised learning technique to classify data points, right? And so one kind of interesting thing of support vector machines is that we can sacrifice accuracy to get better boundaries. And you can kind of think about like maybe why this might be true. There's certain data sets that you're just never, in most data sets, I should say, you're never gonna get 100% accuracy, even if you could draw a perfect line. One is overfitting, but sometimes those data sets don't really exist where you have a clear boundary drawn around it. So it might actually make more sense to say, well, let's go ahead and make a nice boundary versus trying to get every single point in the right side of the classification. So support vector machines allow you to really adjust and say, hey, I really care about the boundary over caring about the actual accuracy of each data point. And this will help us prevent overfitting, like we saw in the decision tree too. So kind of nice thing to have. So kind of a quick question, you guys. When would it be better to have a defined boundary over accuracy? Kind of just think about that just for a second. Just think what situations make more sense where you would care about what makes the part different versus actually finding each individual class. Okay, so just kind of keep that in mind. All right, so some motivation. So I'm going to kind of show you some data set here, and note this is just the iris data set that I'm using over and over again, as you probably noticed, because it's built in, it's nice, easy, and small. So I'm just kind of building this part, and I'm just going to scatter plot. I'm actually going to this here. Yeah, I'll go to scatter plot. So I'm going to just plot, can't talk. I'm going to use the targets. So basically there's only 2 targets, so make it nice and easy. There are technically 3 different targets or 3 different classes for iris. I'm just keeping it as 2 different ones. And I'm going to plot 2 different lines to say, how they classify. So I run this guy. You can see all the purple ones are on one side, all the yellow ones are on this side, and we have 2 different lines here. And just looking at these 2 different lines, this orange line and this blue line, which would you say does a better job at classifying these 2 different points or these 2 different classes?
The red?
The red one, this one right here?
Uh-huh.
Yeah,
Just
okay.
because the blue
So
is too close to that purple data point there.
yeah, blue's too close to that. Give a thumbs up if you agree with Giovanna. If anyone disagrees, just give a thumbs down. Okay. I think most people said thumbs up. And yeah, you're right, Giovanna, right? You probably would say this is probably the better one right here. You intuitively understand it. Note, however, both of these two things have 100% accuracy, right? In the sense that above or to the left is purple and to the bottom right is like yellow. So we know those things are like being classified well, but there's a little subtlety that's like, you know, like, well, which line is better, right? And we kind of saw this before with like linear regression, right? And saying, you know, like, oh, find like the best line and best fit. And it's kind of similar to what's going on here. We're kind of finding the line that best separates them. But note that it's not just about being the best separation. It's also like, you know, what makes the most sense. And you can imagine, like, you can probably picture, like, just from this plot of points, you can probably imagine at the very least, it's probably going up right here. It technically could go off to the side here. We don't know what's going here, but it looks like it's more or less kind of vertical. And that's what this line's kind of capturing here. It's kind of saying, well, it seems to be more going vertical here, and that's kind of like where it's leaning against, even though it could technically go more where this blue line is, and it would still do a decent job. So the main thing is that accuracy isn't everything. So we could say basically these line classifiers have the same accuracy, but they're not, we know intuitively that one seems better. Like, I think most people can kind of get that feeling from what all we've seen already. And basically it comes down to the boundaries are important, not just what is classified as yes or no, or, you know, different classes. The boundaries are just as important. And again, it's kind of comes like with overfitting. So how can we define a better boundary? Like, how would, kind of just asking you all, like, how would you try to like explain what a better boundary is? You want to take a stab at that? Yes. So I think this is not, it's, I think for most people, you can probably tell very quickly which of these two are like the better classifier, but to formalize it, it's not really easy to like just express that. Be like, oh, you want these things. It's kind of like, you might say something like I want the points far away, but still like within the classification. Like that might be something like there, but it's like, how do you say that, you know, formally and everything like that. So we're actually going to talk about how we do this. So the main thing is saying, you know, we want it far away, this distance from the line. So we want data points as far as possible away from this line. That seems to make sense, right? So now obviously there's going to be some extra part to it, because like far away could just be, oh, I want it as far away as possible. Oh, I could put the line way over here. And that doesn't help us at all, right? It's going to misclassify everything. So we still want some things like, well, we want it to classify, but if all these ones are different classifications, like you can imagine like a line going like this way, so now we have 3 different lines, you would still probably prefer this middle one because it's still far away from the other points. It's got a nice buffer in between. And this buffer, this kind of like distance from here to here, or if you measure for this blue line from here to here, this is going to be called our margin. And essentially, we're going to make a large margin. We want to have as large of a margin, basically as big of a buffer as we possibly can, while still doing a good job classifying the data points. Okay. So this is where I get to show a little more code. So going a little bit further, here I'm basically plotting that same data set right here with the blue and purple, but I'm using just, I think, just the orange line right here, this orange or red line. And I'm also drawing these margins. So if I run this here, you can kind of see a little bit these margins. So you can see is that we have the blue line, which was our old like orange line or red line. And I have these 2 other parallel lines. I just made these made them parallel, so they're a little bit further away. And you can see here is that this blue line does a pretty good job of classifying, but actually all 5 of these lines do a pretty good job classifying, saying, oh, this is purple, this is yellow. But the important part here is saying, well, this blue one has the biggest margin. And that's what these yellow and red lines are representing right here, is that they're trying to say, look how far away these points are. Now note that I could extend these margins even further, and they might actually have some points cross over into this margin, but that's okay. Like, we're just saying, like, you know, how far, and you can imagine these margins getting like kind of like extending outward, but we're just trying to emphasize, like, you know, how much of a space do we have between these 2 different classes. Okay, does that make sense to everyone? Any questions at all? Okay. Yeah. So I want to really drill into your guys' head is that support vector machines are all about the margins. It's like they're really trying to focus on that, and that's how they avoid overfitting essentially. So how do we kind of go from here, or where do we go from here? So we can kind of formalize this and basically say there's kind of two ways we can mess up a support vector machine or just classification. One is just saying if we drew the line bad, right? It's like basically like imagine there's a yellow point over on this side over where the purple is. We misclassified one of the yellow points, right? So if you imagine, I'm just gonna kind of ad hoc draw this right here. Imagine we have, I could actually use yellow, draw. There we go. So imagine we have like a yellow point right here, right? So instantly by having that yellow point here, this blue line, right? Remember the blue line's our actual model, is going to drop in accuracy, right? It's not going to do as well, right? But you might argue, actually going to draw a little bit over here. You might argue, you might say, well, okay, let's draw a new classification line. Like, I'm just gonna use this green right here. And I draw a new line like this, because now, and imagine that's straight, okay? So imagine this straight line going forward right here. You're like, well, okay, like this would do a better job of like, we now have 100% accuracy. Would this be a better model still? I see a little, I saw a head shake. I think I saw Giovanna kind of raise her eyes like, I don't know, maybe. Like, and that's the thing. It's like, well, it depends what you care about. If you care about the accuracy, this green line's great, right? But if you care more about saying that margin, saying like a good boundary, it might make sense where this may be just a mistake, or maybe this just like, there tends to be like certain times where the data points will kind of cross over, but there's not a good way to determine it. So maybe if I get like more data points, like I research more, I find actually there's more purple over here. So maybe there's a chance like, okay, maybe this yellow is actually not a good spot. Like it's just by chance just happens to be over here. There's a whole bunch of reasons why this yellow doesn't really matter as much as we make it look like. So in this case, we actually are saying, well, okay, for this blue line, we're caring more about how big of our margin is versus our accuracy. And that basically comes down to say, we have two different points. We have say, how many are classified and how many are in the a bad boundary. So like within the margin. So like how many points are kind of getting to that margin. We want to say that's our error. And so you can actually formalize to say, okay, we have the total error, which is what we'll minimize. Remember, we always want something like the cost function, the loss function. We want to minimize this thing, right? And that's what this is the thing we're going to minimize. We're going to minimize the total error, which is basically how many, the error classification, how many points are misclassified, but then also how big is it, like how much is our, like, let's say this, the error within our margin. So like what's getting messed up in this margin, and we'll classify like how we define this exactly. But you can kind of imagine it's like, okay, there's some importance to the margin by itself. Okay, is it all making sense to people so far? Okay, I think I see some nods. All right, any questions? All right, cool. So kind of going into like, okay, the main thing is like, all right, we can understand how to do classification error because we've been doing that for a while now. But the big part is like, how do we define this error margin or this margin error? And so kind of go back to remember when we made like linear models, and note that I think the curriculum even shows something like this, but like notice like WX plus B, this W is representing like a matrix in this case. Essentially, it's like, imagine all the weights, and we call it W being like weights. So you can imagine this would expand out to something like, if I were to draw this all out, this first equation would be something like W1 times X1 plus W2 X2 plus, so on, however many weights we have, plus B equals 0. Okay, so that's essentially what this first equation is representing. And we're trying to figure out, what's the best W to make that certain line. So what we can do is say, okay, this is our first line. This is the blue line right here. Wx plus b equals 0. That is going to be our actual blue line. And then we can say, as we kind of extend outward, this Wx plus b equals 1. If I drew this line, does anyone have a guess like what this Wx plus b equals 1 going to look like? So I'll give you guys a multiple choice because I know no one wants to take that dive right now. But do you think the line's going to look like this? Do you think the line's going to look like this? So I'll call this line A, line B, or like line C. Let's say this. So give me I should say, let's say this is number 1. I should just use numbers since you guys can do numbers. This is 1, this is 2, and this is 3. So just kind of showing with your fingers, what would Wx plus b equals 1 look like? 1, 2, or 3? I see people thinking. Sorry. Okay, I think I saw some people already kind of go through. I know some people were kind of like, I'm not really sure. I might not want to commit to something right now. That's perfectly fine. It turns out this will actually be something like number 2. We essentially will get parallel lines. And the way you can kind of think about this is like, if I just like -1 over here, that's like adjusting it upwards. So like we're just moving that line up or down kind of deal. So maybe this wasn't exactly right. It should really be like something like this. So kind of trick question, right? But the idea is that it'll be in parallel lines versus it won't be perpendicular. It won't be whatever I randomly made up over here. The point is that these parts will actually add up different lines. So what this looks like in code. And so I just copy the same code, but I just adjust the margins so they're a bit larger. You can see like this would be like Wx plus b equals 0. This might be Wx plus b equals like 1 or something like that, and equals 2, equals 3, and going further and further and further out. And so the idea here is that we can actually use this to say, okay, how many points are actually in this margin? So what we'll do to do this classification error, we'll actually start from this part right here and say, okay, going to the left right here. So we're gonna say this is the yellow side, right? This is like the yellow stuff and this is the purple stuff. We start from this one, Wx plus b equals 1, and we say everything to the right here. If you have a yellow over here, this is going to be an error. So actually, if a yellow is in this spot right here, that will be considered an error. Does that make sense? So this is our margin error. Remember, it's not our classification. And basically say we want things out of this margin. So if we have a yellow spot right here, this will actually count against us. And then note as we kind of go over here, we don't really care about these errors because that's where they're supposed to be. But if we had more like a yellow over here, a yellow over here, a yellow over here, these should be weighted a lot more, right? So as we kind of go off to the left here, away from the yellow side, we would want these yellow things to be counted more and more over on the side here. You can technically go even the other direction and say, well, what if we counted these parts? But these would be counting less and less and less and less, right? So the idea here is that we will quantify the margin by saying how many points are not in this, like basically in the wrong side over here. And that will basically not just help us with classification, but also with that margin where if we have a bunch of yellow spots, I know it's blue, but it's a little bit easier for us to see this yellow spots in this margin here, these will be errors and these should actually say, oh, your margin's not very good. Your margin needs to be even smaller, or you need to define your line in a different way so your margin looks better. So if I imagine of having a bunch of yellow like this, then in that case, it looks like this blue line right here probably wouldn't do a great job. It probably would make more sense for the line to go this way. So that way the margin's relatively small, but still doing a good job classifying the points. Okay. Does that make sense to people of how we're building up this margin error? Okay. Give me a thumbs up if that makes sense. Sideways, you're like, I don't know. Thumbs down, you're like, I'm lost. Okay. I see some mixed response. I see some thumbs up. I see some sideways. So kind of simplifying this a little bit further, because I know it's a lot kind of like, wait, what are we doing? The main thing is that we already know what classification is. We're not completely ignoring that. And we're saying, how do we build this error, this margin error? And the main thing is saying, are there points that are past this other, like basically a buffer? So we kind of go one buffer over here. And these points should count more and more against being like, oh, your margin was bad. Versus, hopefully that makes sense. Basically, you're starting, instead of starting from the middle, you're starting from this point right here. Oops, I can't draw. You're starting from this point right here and saying, okay, that means what will happen then is like, if I start at this point right here, that means this guy right here is an error. It'll be a less of an error than if it was over like here, right? But it'll still be considered an error. And essentially we define that within parallel lines going through. Say, okay, the points that are over in this area right here get multiplied, let's just pretend, get multiplied by like 2. Or this one over here gets multiplied by like 4. You know, as we kind of go further and further into there, we say, okay, these should matter more and more and more and more. And that's essentially what this margin error is building. So this gives us a little, like, it helps prevent us making a line, this blue line here, and making that line with that still has, like, technically it's classifying things right, but you have a bunch of yellow points within this margin. So basically you're still punishing these points, even though they're classified, quote unquote, correctly. Okay. So I think once you kind of have that idea, it's like, okay, like basically these things in this margin part are going to get, what's it called? Punished, essentially. That's going to be what we define as our margin error. Okay. And I'm not going to really show too much of the mathematics of that by itself, but you can see here, oops, I'm still drawing stuff. There we go. Okay, so essentially this from right here is basically saying how far away is it from this point, and we can just add up this error all together. And this is where the curriculum kind of goes through a little bit of, like, you know, saying, okay, we just want to create like this margin, and this margin is determined, saying how big is our margin. It's basically adding up all the different, you know, errors essentially in those different little margins, and this will basically build it up. So don't worry too much about this, like how to build this part directly. If you want to go into more detail, the curriculum kind of explains parts of this, but just know that essentially knowing where the points like land in here can help us define what our margin is. What's really cool about this is that, remember, we're talking about just support vector machines. This definition is the same thing as the L2 regularization. So remember back, like, if you guys remember back to logistic regression, do you guys remember L2 regularization, what that was doing? Give me a thumbs up if you guys recall that. All right, that's all right. So basically our regularization was to prevent overfitting. So if you remember back, like when we calculated our costs, we normally would have something like, okay, let's see how the errors are for, like, you know, y minus y hat. So y hat is our prediction, y is our actual, and then we square this part. And you're like, okay, we can see how well it performs. Well, we can add an extra term here called a regularization term right here. It was something like this lambda. And we can basically add this little extra factor. It turns out this is the same thing as if you were doing L2 regularization, which would be a squared point right here. So it turns out it's the same thing. That's why this ends up being a way to avoid overfitting, because that's what regularization is doing as well. So anyway, that's mathematics on that part, like where that comes from. But we're not gonna dwell too much because there's more in the curriculum on that. So then once you find our errors, okay, we have our margin error defined. We're saying the total error is the classification error in the margin error all put together, right? We can just build up our gradient descent, and then we use our gradient descent to just minimize that error term. Okay, make sense? Okay, yeah, and remember, basically gradient descent, we always need something to say how wrong the model is. That's essentially what gradient descent is really doing, is saying, hey, let's just tweak the model to make the error even smaller, the cost smaller, the loss smaller. And so that loss is going to be determined by the margin error plus the classification error. Okay. So this leads us to our hyperparameter C. So our hyperparameter C is this kind of factor that we allow, like basically you can imagine like a dial where we turn it, say, do we care more about the margin or do we care more about the classification? And so this hyperparameter allows us to say, okay, here's the total error. And then saying not just the error of classification plus the margin, but we multiply it by some number. And this basically means that we're going to care more about the margin or to care more about the classification, depending how big C is. All right. So kind of a quick question, right? So just to get a feel for like what the C is doing. If I make C very, very large, what errors do I care more about based on this equation?
Classification.
Yeah, classification is going to get a larger error. Basically, even the smallest little error in classification is going to make this error total super huge because C is super huge. So essentially it means that, oh, we care more about classification over the margin. If we just did the other way, we'd care more about margin. Okay, cool. And then again, remember this error total is what we're directly using gradient descent to minimize. We're trying to minimize the amount of error. It's just that their error now is not just about classification, but also about that margin, which basically is trying to build our boundary. Cool. All right, so before I move on to the next part then, which—
I have a question, Victor. So would C be negative if we wanted to prioritize the margins, and it would be 0 if they were equally weighted?
You wouldn't put it to 0. It usually goes to 0. Yeah, usually we say 0 or higher, because then if you have, I guess you could technically change C to negative, but that's usually not what we're talking about. Usually say, do you care about classification at all? If you care just about the margin, or if you care more and more. So you would turn it up from 0 to a higher value.
Okay, thanks.
No problem. No problem. Yeah, so anyway, this is something called a hyperparameter. So I don't know if we mentioned hyperparameters. Give me a thumbs up if anyone knows what a hyperparameter means. Okay, so this might be the first time we're really talking about this. We might have inexplicitly kind of talked about it, like, you know, kind of in the background. But a hyperparameter is something that is not used to actually classify. It's used to help train. So if you imagine this error total is not going to directly affect like where, like how well it classifies. Like it's not part of like defining the line. It's just saying what we use to, it's helping us decide how to do the gradient descent. So a hyperparameter is more about a parameter that changes how we use machine learning to approach the classifier. Does that make sense? Versus a parameter, like let's say we go back to linear regression, a parameter might be like the actual weight of, or like the coefficient of a feature, like multiplied by a feature. So those are like direct parameters, like, oh, these things actually affect the model. Versus a hyperparameter is being used to adjust how we learn. Like, so if you imagine, if you adjust the C here, this will ultimately change your support vector machine, your classifier, but it's not a direct parameter in saying, oh, we change C to this way, it instantly will like move the line this way. It's just, oh, in the next round of gradient descent, it'll move it in a certain way. Does that make sense? Okay, so that's why we call it hyperparameter. Basically, it's like one level removed. Okay, so this leads us into, or any other questions before I lead into kernel trick?